Hello, hello, all my beautiful pre-calculus minds out there. Today we're going to talk about some odd and even functions. Let's take a peek at a few examples here. I have taken the liberty of creating some functions that are odd, some functions that are even, and some graphs that are neither odd nor even functions. So if you take a look at the even functions, hopefully you'll be able to discern something that's happening with both of those graphs over here. I'm talking about these two graphs, the even functions on the left-hand side. They have a common characteristic, those two graphs. On the right-hand side, these odd functions, they have something in common as well. And the functions that are in the middle here, these neither functions, or neither, I should say, because the first one up here, that circle, isn't even a function at all. So if you don't have a function to begin with, then you're not going to be an odd function, you're not going to be an even function. So it's kind of a trick question a little bit, but so you're going to have to make sure to test to see whether or not the graphs that are given to you are functions at all. And if they are functions, then you can decide whether or not the function given to you is even or odd or neither. Okay, so let's take a peek at some of the features that we're going to be having here. Let me squish this down just a little bit and scroll up here. Even functions have what kind of symmetry over what? So I'm hoping that you can take a peek at these two graphs over here, and you can just imagine that you could have this line going right up and down here, this y-axis, and you can see that the function can be a mirror image of itself over the y-axis. Same thing down here. This is definitely a function as well. I haven't even said what a function is, but I hope you know that each x value has exactly one y value. So both of these are even functions because these two functions are symmetric over the y-axis. So let's go ahead and fill this in. Even functions have something we're going to call line symmetry over the, and this is y-axis. Okay. Just taking a peek here at something else I made a comment on. Quadrants 1 and 2 are mirror images. So here's quadrant 1, here's quadrant 2. If I take quadrant 1 and just flip it over the y-axis, I do indeed get the points that are in quadrant 2. Likewise, quadrants 3 and 4 are mirror images. There's not much down here for quadrants 3 and 4, but here's quadrant 3, here's quadrant 4. They are mirror images of each other over the line of y equals x. So the graph is symmetric over the line of y equals x. Same thing on the top. Here's quadrant 1, here's quadrant 2. You see how quadrant 1 points can just get flipped right over to quadrant 2? That means that we have symmetry, line symmetry over the y-axis. Likewise, everything here in quadrant 3, everything here in quadrant 4, they match each other as far as mirror images over the y-axis goes. Okay, so moving on to odd functions. Odd functions, oops, I'm sorry about that. Odd functions have blank symmetry about the blank. So I wrote down here, quadrant 1 rotates around to quadrant 3. Let's take a peek at this one here. Quadrant 1 up here for this odd function. Here's quadrant 1. If quadrant 1 were to rotate down over here to quadrant 3, then I would not have a mirror image, but I have a rotational image. And that rotation has to happen over the point 0, 0. So it has to happen about the origin. So basically, if I could take a pinpoint and I could like push it straight through at 0, 0, I could literally rotate this picture 180 degrees. It would be upside down 180 degrees, but it would fall right back on top of itself. And same thing here for this odd function. Notice that 0, 0 is a point on the odd function. If I put a pinpoint right here and I rotated this whole picture 180 degrees, then it would fall right back on top of itself. Thinking in particular, if I took this point, and I know I'm not sure you can see it or not see it, let's just zoom in here. This is the point negative 4, 6. If I took negative 4, 6 and I rotated it 180 degrees, I would get this point 4, negative 6. So that's what's happening with odd functions. Odd functions have rotational symmetry of 180 degrees because you've got to go halfway around a full rotation, and it's about the origin. So let's come back here and fill this in. Odd functions have rotational symmetry about the origin. And you know, I'm going to go back and I am going to adapt that rotational. So I'm going to literally, I'm going to circle this and just push it over so that I can write something else here. And I might just have to eliminate it altogether because I want to say 180 degree rotational symmetry about the origin. So I need 180 degree, I need to be specific enough, 180 degree rotational symmetry about the origin. So quadrant 1 will rotate into its opposite quadrant, or the quadrant that's 180 degrees away from it, into quadrant 3, and vice versa. Quadrant 3, if you had something in quadrant 3, you could think about it rotating into quadrant 1. I could take this point 4, negative 6. I said quadrant 1, I meant quadrant. Yes, okay. So here's quadrant 1, 6, 2. If I rotate this 180 degrees, I would come here to negative 6, negative 2. Or I could think of taking negative 6, negative 2 and rotating it 180 degrees and coming up with 6, 2. Whichever point you start with, you're going to end up with its corresponding image in the opposite quadrant. Okay, so let's see if we understand a little bit about this. Let's go through some questions here. I lied. Mathematical definition of an even function, and then we'll go through some questions after we do the mathematical definition of even and odd. It's important that you realize this is the mathematical definition. Everything we talked about up here is not the mathematical definition. It's just something you visualize by looking at a graph. So the mathematical definition of an even function says that a function f is even if for each x value in the domain, it has to be for each x value in the domain, not just one, not just two, but each of them, f of negative x equals f of x. And that's a pretty easy mathematical definition. So let's see what it means. Now, I just took the liberty of copying one of the functions up here that was even, like this one right here. I grabbed this even function, this one, and I just copied and brought it down. So we're going to use the same picture. And we're going to talk about f of negative x is equal to f of x. For example, if my x was, let's say, the number 7. Okay, if x is 7, then f of negative 7 has to equal f of 7. Now these are y values. The y values have to be equal to each other. So f of negative 7, if I look on my graph over here, f of negative 7 is 4. And f of 7 is also 4. So that works. Okay. If I chose, instead of 7 as my point, let's say for instance I chose x equals negative, let's go for negative 11. If I said x equals negative 11, then f of my negative x would be a positive 11 now, and would that equal f of x, which is negative 11? So let's see, f of 11 is down here at negative 2, and f of negative 11 is over there at negative 2. So negative 2 equals negative 2, and that of course checks as well. So what we're saying here is that it doesn't matter whether the x value is to the left or to the right of the y-axis. If you pick an x value to the right of the y-axis, like 3, then you're going to get the same height over here on the left. And it makes sense because we are reflecting over the y-axis, so when you reflect over the y-axis, only the x value changes and the y value stays the same. So let's see what we're looking for answers on these questions here. I'm basically paraphrasing the mathematical definition of an even function for you so that you can see it and hear it in different ways. If a function is even, then changing the sign of any input value results in what? If I take my input value, like 7, and I use negative 7 and positive 7, what kind of a result do I get from my output? So changing the sign of the input results in, and I'm going to zoom in here so I can write no change in the output. So I end up having no change in the output, which means the output values are the same even though we are changing our input value. So with the second thing here, that's good there. With the second topic right here, with an even function, again, opposite input values, or x values, yield what? Okay, if I take opposite input values, like this negative 7 and this positive 7, what kind of values do I get for answers? Well, I get equal values. Okay, so they yield equal output values. I'm just going to follow the same format that I have with my question. Equal output values. And then in parentheses, I'm going to say or y values. All right, I know that the input values are the x and the output values are the y, but it doesn't help to reinforce it and state it here and there. Okay, another way of saying this, thinking about this, paraphrasing this, would be to say that with an even function, negating the input value. Now when you negate the input value, you apply a negative sign to it. You negate it, you apply a negative. So if I negate 7, I get -7. If I negate -5, I have +5. So basically it just means switching the sign. Okay, so with an even function, negating the input value, what negates the output value? And I'm going to just tell you that that is never. Okay, that never happens. If I try f of, let's say, -7 and I have 4, then f of +7 is exactly 4 again. It does not change. So negating the input never negates the output. And that's just, 3 different ways to paraphrase the mathematical definition of an even function. Okay, let's go ahead and hit the mathematical definition of an odd function and see how that changes. You know it's going to change. So the mathematical definition of an odd function says that a function f is an odd function if for each x in the domain, not just one x, not two x's, not three x's, but every single x value in the domain of the function of f of negative x equals negative f of x. So this is kind of important. We're talking about if we change the value of the x's, what happens to the y's, and same thing for the even function, because the minute I say f of something, I'm dealing with a y value, right? I'm dealing with some kind of a y value. Okay, so let's take a peek at our picture and let's talk about this. I just want to give some examples about this right here. So let's go ahead and pick x equals, notice I took the odd function from the above example, or one of them. I think I'm going to go ahead and pick this point right here. -4, 6. I'm going to talk about that. So x is -4, right here. X is -4. So I'm going to say f of negative x. F of negative x equals negative f of x. And let's see if this is true. Okay, so the first thing I'm going to do is negate my x. So this is going to be -4. See how that is? Or the opposite of x, if x is -4, is just 4. And this should be the opposite of f of 4, f of -4, sorry. Maybe it would be nicer if I just chose a positive value for my x, and then you could see it a little bit more clearly. But I'll do that in just a minute. So this gives me f of 4. I have to look at my graph, and I have to find f of 4. F of 4 is down here, and that gives me -6 is equal to, now I'm just going to copy that negative sign, and now I'm going to find f of -4. F of -4 is back over here in this point. F of -4 is 6. So -6 equals -6, and that is definitely true. So I'm going to pick another x point. This time, instead of picking a negative x value, I'm going to pick a positive x value, which I probably should have done to begin with. Let's do, let's try 9, -2. So in this case, x is equal to 9. So I'm saying, what happens if I test f of -x? Will I indeed get the opposite of f of x? That's my question. So if x is 9, then I can just put a 9 in place of this x right here. So this gives me f of -9 equals, I'm wondering whether this is true or not, negative f of 9. So I got to go back over here and look for f of -9. F of -9 in this problem is right here. F of -9 is, oh, that's not true. F of -9 is way over here, right? -9 is my x value. You see it? -9, x equals -9. So when x is -9, my y value is a 2. I'm going to come back over here and put a 2. And now I want f of 9. So I look over here for f of 9. F of 9 is on the right-hand side of the y-axis, and the y value here is -2. So I'm going to come back over here. I'm going to put -2 in for f of 9. But this negative on the outside tells me to negate that answer. So if I negate that answer, I do indeed get 2 equals 2, and yes, it works. Okay, so this odd even stuff is more or less a drill in notation to try and get you to make sure you understand what f of -x means, what negative f of x means, what f of x means, and all that, and keeping it straight in your mind. But let's paraphrase the concept a little bit like we did with the even functions. And let's talk about this odd function idea. Okay, I'm going to erase this and this. If f is an odd function, then changing the sign of any input value results in what? So if I change the sign of the input value, so instead of f of x, I pick f of negative x, what does that do to my f of x? And you see this minus sign that's right on the outside of it should tell you that it's going to change the sign of the output. So I'm going to zoom in here and I'm going to write results in a change of sign in the output. Very good. So if you change the sign of the input, you must change the sign of the output. Look at this again. Let's talk 6, 2. So 6, 2 is a point on f. If I change the sign of the 6, then the sign of the 2 changes also. Boom, right there. Let's do it again with 9, negative 2. If I take 9, negative 2, and I change the sign of the x, that gives me negative 9. What happens to the 2? It changes sign as well, and I get positive 2. So if you change the sign of the x, you also change the sign of the y. Does that make good sense? Okay, I hope it does. So if you have an xy point and you change the sign of the x, then you also have to change the sign of the y. Suppose I should go back up there and do that for even, but I'll do that in just a minute. Okay, with an odd function, opposite input values, or x values, yield what? And yeah, I hope you say opposite output values. So let's go ahead and write that, opposite output values. And in parentheses, I'm going to just say or y values. Okay, opposite y values. If you change a sign or you talk about the opposite input value, then you have to talk about the opposite output value. Okay, paraphrasing again. With an odd function, negating the input value, what negates the output value? And this is a simple always. Whoops, spell always right, Gina. Always negates the output value. Okay, so let's just make sure we're clear on this. For the mathematical definition of an odd function, and this would be a test question as well, if a function f is odd, or a function f is odd, if for each x value in the domain of f of negative x equals negative f of x. That's really important. Negating the x negates the y, the original y. Okay, I'm going to come back up here into the odd, into the even idea here, and the even function definition says a function f is even if for each x value in the domain of f of negative x equals f of x. That means that if I change the sign of my input value, so I start with an xy point, and I change the sign of an input value, so I'm going to have negative x right there. Not sure why I did that. Okay, that means I don't change the sign of the output value. I leave it alone. So if you have an xy coordinate point that's on f, that means that negative x comma y also has to be on f. Let's test it with these values here. Okay, let's take 6, 1. So if I have 6, 1 that's on f, that would mean that negative 6, 1 would also have to be on f. Is it? Yeah, it is right there. Okay, so there's lots of different ways to think about this, but only one way is considered the mathematical definition of the even function itself. Okay, now we're ready to drill some questions. Okay, so we have all that information. First thing I think we do before we drill the easy questions is actually do some proofs. This might be the first time in your life that you're doing a mathematical proof, but when you hit college, you would do proofs almost in every single class. So it would be really nice if you had a little practice in high school playing around with some proofs. And that's what we're going to do. Okay, so I'm giving you some step-by-step directions here, which is not like me, but I'm going to do this anyway. You can analyze the characteristics of a graph to determine if it is the graph of an even or an odd function. But how can you analyze an equation of a function analytically in order to determine if the function is even or odd without looking at the graph? Okay. Step 1. always start by substituting negative x into the function. In other words, test f of negative x. Step 2, simplify the equation. Step 3, ask yourself, is this result equivalent to the original f of x function? If so, state that f of negative x equals f of x, and then say, therefore, f is even. So the little ... means therefore, and the little box means you're done. If not, however, indicate to the right that your answer does not equal f of x, and therefore f is not even. And then you continue to step 4. You're not done. Step 4 says, ask yourself, is this result equivalent to the opposite of the original f of x function? If so, you state that. You say f of negative x equals negative f of x, and then you say, therefore, f is odd, end, with a little box. If not, then you have to state that f of negative x is not equal to negative f of x, and therefore f is not odd. And your final answer can say, therefore, f is neither even nor odd. Done. So let's do a few of these. You can always revert back. You can put those in your notes. You can rewind your video, whatever you need to do. But let's jump into a few of these problems. And we're going to prove that f of x equals 3x squared plus 4 is even. Step 1 is the same no matter what, okay? Because the question is always, what if I negate my x? So we're going to take f of negative x and literally put it into the problem everywhere you see an x. So really, I should have left that blank, and I would say f of x is equal to 3 times x squared plus 4. So whatever my input is, that goes in for the x value. So I want to test negative x. I put a negative x in everywhere. And this next step you might want to do, you might not want to do, but I tell you what, it has helped me and helped many students not make mistakes. So when you square something, you write it down twice. So I'm writing it down twice. And now I'm going to simplify. I'm still in step 2. This gives me a negative times a negative, gives me a positive, gives me 3x squared plus 4. So now I'm up to that step 2 part up here, or step 3 part up here, because I've simplified step 2. Is this result equivalent to the original f of x function? So is this equivalent to the original f of x function? And the answer is yes. So at this point, I have to write f of negative x equals f of x. This is the mathematical definition of an even function. So therefore I say, therefore, f is even, and I put a little box down here and I fill it in and I say, I'm done. That's the end of the problem. And since the whole thing said prove, this whole thing is my answer. So if I were to have to highlight anything, I would highlight the whole entire work. Okay? Example 2. As a matter of fact, why don't I just do that? Why don't I just highlight this whole thing? Very good. Example 2 now. I want to prove that f of x equals 2x cubed minus 8x is odd. So I know that that's a function. It's a Cubit function. So I'm just proving that it's an odd function. First step, test f of negative x. In other words, negate the input. So this is 2 times my input cubed minus 8 times my input. My input is negative x. Now I'm going to write it out. Many of you don't need to write it out, and that's fine, but I'm not going to make a mistake, I hope. So I'm going to make sure that I do something to prevent errors. So this gives me, notice how on the left-hand side of this equal sign, I just copy, 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 copy f of negative x. That never changes. I only play with the right-hand side. So I have 3 negatives right here. So 3 negatives is going to give me a negative, and it's going to give me x cubed with the 2 following, okay? Minus minus is going to make a plus 8x. So is this the original function up here? Is this the original function? I hope you clearly say no. Okay, this is not, and that's why I put this in on the right hand side. I'll go back up here for you to see it here. Is not f of x, therefore f is not even. So this is not f of x, therefore f is not even. Even is always the first thing you test. So now the question is, that next part says, is this the opposite of what you started with? So you actually might want to just kind of like do a little thing to the side and just say the opposite of f of x would be negative 2x cubed plus 8x, or maybe we could put a minus sign on the outside of the whole thing, 2x cubed minus 8x, and then distribute that negative symbol. So did I end up finding the opposite of f of x? And yes, indeed I did. So I'm going to say f of negative x equals the opposite of f of x. Therefore, f is odd. And I put a little box. Now, if I tell you to prove a function is odd, don't end up proving that it's even, because it's not. I'm not giving you a trick question. If I say prove something's odd, it is odd. Get to that proof. If I say something's even, it is even. If I say it's neither, it is neither. I am not tricking you. When it's up to you to decide, I will ask you to decide yourself. Okay, so this whole thing is your proof. Everything from beginning to end. Highlight everything. Very good. And we move on. Example 3. Here we go. Prove that f of x equals 5x squared minus 3x plus 2 is neither even nor odd. So I'll tell you what the last step is going to be. The last step is going to be, therefore, f of x is neither even nor odd. Okay, that is going to be the last step, because that's what I've been asked to prove, so that's going to be my last step. Just like in the one above it here, I was asked to prove that f is even, and that's my last step. I was asked to prove over here that f is odd, and that is my last step. Okay, so let's start on this, and I probably will end up not in that exact spot, so I just wanted you to know that that would be my final thing there. Okay, so here we go. First step is to take the original function and negate the input. So I'm going to put negative x in here. When I put a negative x in here, it's a very generic test. It means that for all x's, this is going to be true or false or neither. So we'll figure this out. So copy f of negative x equals. Keep copying that over and over again. Do not change the left-hand side of this equation. So this is 5, and this is being squared. So negative x, negative x. I guess I just will copy this for a minute here. And now I'll simplify this. F of negative x is equal to, a negative times a negative is a positive, so this gives me back 5x squared. That's good. A negative times a negative here is a positive, so this can become 3x and then plus 2. So my question is here, did I get back the original question, the original function? And I did not get back the original function. This is not the original function f of x. Therefore, f is what? Not even. I might have to shrink this a little bit or push it over. Let's see about just pushing it over for a second. Don't want it to run into my next question. There we go. All right, so now I need to ask myself, is this the opposite of the original function? So the opposite of the original function, I don't know how much room you have up here, but the opposite of f of x would be, and you go through and you change your signs, negative 5x squared plus 3x minus 2. Is that what I got? No, it is not. So this is not the opposite of f of x either. So therefore, f is not odd. So I've proven that f is not even, I've proven that f is not odd, and now I can say, therefore, f is neither even nor odd. And I'm done. That's it. Okay, so you can call the function f, or you can call the function f of x. Okay, either way is fine. Technically, if we wanted to get really technical about it, it is the function f. Okay, it's not the function f of x, but I'm not going to argue that. I'm not even going to discuss it right now. So this is, let's highlight everything here, all the way over. And I don't expect people to highlight like that. Okay, so highlight your answers, solid highlight everywhere you go. Okay, moving on to example 4. Prove that f of x equals 4x to the 2/3 is even. I'm telling you it's even, and I want you to prove it. Okay, So what we're going to do, and perhaps I need to go to the side and just talk to you about this for a second. This is like y equals 4x to the 2/3. So x to the 2/3 is x squared under a cube root sign. And that should be a 4 right there. I don't know why I made it an x. So this is under a cube root sign. All right? So just so that everybody understands what's going on, I am going to negate my input, and I'm going to see how that does not change the output whatsoever. So I'm going to put a negative x in here, put a negative x in here. By the way, the even concept means that the output never changes. So whatever you would typically have for your y value, which is this, that's the answer I'm going to get when I'm done with this problem. So f of negative x equals 4 times negative x to the 2/3. I'm going to show my work on this, and I'm going to make sure everything's clear. This is the cube root of negative x quantity squared. So I'm going to go a little bit more in detail and write it out. Okay, this is still the cube root of negative x times negative x. Negative x times negative x is just positive x squared again. So this is the cube root of x squared back, which is x to the 2/3. And is that the original function that I had to begin with? And your answer is yes. F of negative x is indeed back to the original function f of x. And now you can say, therefore, f is even. And put a little box, because at the end of all proofs there's a little box. Feel free to look into your book. Feel free to figure that out anywhere else you want to find it. Have you ever read an article like in the Time magazine or the local paper or something that says continued on page whatever, and then you get to that page and you find the continuation? At the end of the continuation, they might even send you someplace else, say continued on another page. But when it's all done, they will put that little dark box. Okay, that means we are done with our proof. Okay, moving on to example 5. Determine if f of x equals the absolute value of 3x quantity minus 5 is even, odd, or neither. So step 1 is always the same. Everybody does the same thing for step 1 all the time, I hope. Input a negative x. Okay, this is going to be the absolute value of 3 times my input minus 5, and my input value is negative x. So copy your left-hand side exactly how it looks, okay? F of negative x equals, this is the absolute value of negative 3x, quantity minus 5. And here is a little intuitive thought process here for just a minute. If I had the absolute value of negative, let's say 7, isn't that automatically equal to the absolute value of 7? Isn't the absolute value of, let's say, I don't know, 12 equal to the absolute value of negative 12? The absolute values really don't care whether or not the number inside is positive or negative, because it has the same result of turning whatever it is positive or keeping it positive, right? Because 12 equals 12 over here. Same thing, 7 equals 7 above. So regardless of whether or not the x value is positive or negative, the absolute value of negative 3x is the same thing as the absolute value of positive 3x. And this just takes a little bit of thought process here for you to come up with that, but you're coming up with it because your purpose here is to see whether or not you get the original function back again, or whether you get the opposite of the original function back again, or neither case. But we certainly don't want to eliminate the absolute values from the problem. So because I do get the same exact thing back again as the original problem, f of negative x actually equals f of positive x, and therefore f is even. And you put a little block down here, like that. Okay, so I'm going to highlight this whole entire thing, because this whole entire thing is my answer, the whole entire proof. And we're going to move on to question number 6. So on number 6 here, we're going to prove that f of x equals 9 is even. So I input my negative x, which means everywhere I see an x in the function, I'm going to put a negative x into the function. However, I don't see any x's in the function. So f of x equals 9 is a constant function, which means f of negative x is going to equal 9 as well. which brings me right back to the original function. So yes, indeed, f of negative x is equal to f of x itself. Therefore, we say f is even. And we put our little box here. Okay. Highlight the whole entire thing. And just to add a little something to this conversation, I know that the whole purpose of examples 1 through 6 here is to prove that a function is odd or even or neither analytically. But I just want you to get an idea graphically what this function looks like in particular. This is f of x equals 9, which means that this is my x-axis and this is my y-axis. F of x equals 9 is right here, something like this. This is y equals 9. And y equals 9 is a horizontal line. F of x equals 9 is a horizontal line. All horizontal lines are indeed even because when you reflect them over the y-axis, they fall right back on top of themselves. So common sense there a little bit is going to, talk you into the fact that f of x equals 9 is even. Over here with the absolute value function, just to talk about something a little bit, y equals the absolute value of x. I hope everybody knows what that looks like. That's one of your common functions. Okay, so if this is my x-axis and my y-axis, I'm looking at going straight up through quadrant 2 and straight up through quadrant 1. That's the absolute value function. If I have a 3 attached to the x, that means I'm going to have a horizontal shrink by 3, or an r value of 1/3, which means that this is going to turn into something that looks like this. Here's my x-axis again, here's my y-axis, and basically I'm going to take that shape and I'm going to shrink it so that it looks like a vertical stretch. Vertical stretches and horizontal shrinks look the same anyway. Okay, and now I'm going to minus 5 from that thing. So I'm going to actually take the function that I just drew, and I'm going to drop it down 5 units. I'm going to pretend that that's 5 units and call this 0, -5. I'm going to draw this up real narrow so that I end up getting the same picture. So this is my x-axis and this is my y-axis. And you can look at this picture and hopefully tell, yes, indeed, that is an even function because you are symmetrical over the y-axis. Okay. All right, moving on. We have a bunch of cool questions coming up to you, okay? So some of these are, you just circle something, some of them are fill in the blank, some of them are true and false, but we're just going to try and paraphrase this concept over and over and over again and hit it from different directions to make sure you're understanding everything that's going on. Okay. Starting off right now, I'm looking at example 7, odd or even, circle one of these things. Functions are symmetric over the y-axis. Now, which kind of functions are symmetric over the y-axis? I'm sure hoping that you're saying even functions are, so you go back and circle. And with an even function, when you negate your x value, it doesn't have any effect on the problem. You're right back to the same height you were. So the height of the function at negative x is the same as the height of the function at positive x. This is the mathematical definition of an even function right here. So finish it up by, and I suppose we'll just highlight this piece. Okay, I kind of want to highlight the whole thing right there, but I'll leave it alone. Question number 8. Odd or even, circle 1, functions have 180-degree rotational symmetry about the origin. The origin is the point 0, 0. That's going to be your odd function, resulting in, okay, what happens if you negate the x? You have to negate the y. So the y value is f of x, and when you negate it, you put a minus on the outside of it, and that is going to be your mathematical definition of your odd function as well. Question 9. Given the fact that f is even, and 8, -6 is on f, or is an element of f, okay, that means it's a point on the function f, then what else has to be on the point of f? So let's see, even function. Even function says if I negate my input, my output stays the same. So if I negate my input, the output stays the same. That's the answer that I want for this problem. And let's just look at it quick, like graphically. This is my x-axis, this is my y-axis. The point 8, -6 would be over here someplace, 8, -6. And if you're going to have line symmetry over the y-axis, because you know you have an even function and you get what that means you toss over here and you end up getting -8, -6. So graphically you can identify it for yourself as well. All right, -8, -6 is right here. Next question, question 10. Given that f of -3 equals 7 and f is odd, now we're talking odd. Odd says if I negate my x, then my y value must negate also. So negating a negative 3 gives me a positive 3, and negating this 7 right here gives me negative 7. So that means that f of 3 has to equal negative 7. Let's just peek at that graphically as well. Okay, let's just go ahead for an xy axis here. Negative 3 is negative 3, 7 would be a point on the graph. Let me see. I'm just going to eyeball it and just say negative 3, 7, just like that. This is my y-axis, this is my x-axis. Okay, so if I have the point negative 3, 7 on my function f, and I know that I have an odd function, that means I'm going to rotate 180 degrees from this negative 3, 7. Right now I'm in quadrant 2, so I got to be down here someplace. When I rotate 180 degrees, I'm going to be at the point 3, negative 7. It's going to be down here. 3, negative 7. 3, negative 7. You can basically really kind of draw yourself some kind of just an imaginary line through the point and 0, 0. Yeah, that was not good. Somehow or another, that was a mighty thick line, wasn't it? I wanted it to be teeny tiny. Okay, let's try it again. Draw yourself a line through the point that was given to you and through 0, 0, and then keep going. So if I wanted to be a little more technical, then I'd be over like this. Here's my negative 3, 7. You go 180 degrees, which would put you on that line that crosses through 0, 0 of 3, negative 7. Okay? Hopefully that helps a little bit too. It gives you another way of thinking about this perspective. Question 11. Given that f of 14 equals 6 and f is even, if f is even, that means that when I negate my input, my output does not change. That means that f of negative 14 also has to be 6. Okay? This, by the way, f of 14 equals 6, tells me that I have an input-output combination that exists on f. So if I have that input-output combination, I change my x and leave my y alone, that would mean that negative 14 comma 6 is also on f. So therefore, f of negative 14 is equal to 6. Okay, highlight that whole thing. Question 12, given that f is an odd function, negative 9, negative 2 is on f, then, let me see, odd says negate my input, so that gives me 9, and when I negate my input, I also negate my output. So this negative 2 became positive 2. Question 13. I'm looking at f of x equals cosine of x is an even function. And we should know that already because you should have an idea what the cosine function looks like. Cosine function looks like this. And at 0, it just goes backwards. Okay, this is my y-axis, this is my x-axis. Okay, so whatever's here, bring it over here, it's automatically here. Whatever's here, bring it over here, is already here. So we definitely have line symmetry over the y-axis. The cosine function is even. So this, like it or not, this cosine negative x is the same thing as f of negative x. So I'm taking a negative x and I'm shoving it into the function. So what does that mean? It should mean that I'm getting f of x back again, the same function that I had to begin with, so cosine x goes over here. So cosine of negative x is equal to cosine of x. And that's kind of important because in the future, if I ask you to find cosine of like negative 2 pi over 3, all you have to do is find cosine of pi over 3. And hopefully you'll remember, or negative, I'm sorry, let me just say that again. If in the future I ask you to find cosine of negative 2 pi over 3, then all you have to do really is find the cosine of 2 pi over 3. They're the same thing. So then you don't have to play with this negative sign, which is really kind of cool. I love that idea. Okay, moving on to the sine function here. The sine function is odd. That's the truth. Sine function is odd because the sine function, if this is my xy axis, and again you already know what this looks like, the sine function does this thing, and it goes right through 0, 0 like it has to. Okay, so if I have this point up here, which would be the point, I know you don't know it right now, but it's pi over 2 comma 1, and I rotate 180 degrees, I'm over here, it gives me negative pi over 2 comma negative 1. So when I negate the input, I also negate the output. So this is f of negative x, which is sine of negative x, and that has to equal negative f of x, which would be negative sine of x. And that's kind of cool and kind of important as well. Whoops, I thought my highlighter was on. That's kind of cool as well because if I were to say to you, find the sine of negative 5 pi over 6, you could say, okay, well, I don't know what to do with that negative, or I don't want to deal with that negative, or I know sine is odd, so I'm just going to find the sine of 5 pi over 6. I'm going to forget the negative sign. When I get my answer, I'll just negate it, and it gives me the same thing. And it's fast, it's quick when you do things like that. Little extra tidbits that make your life in mathematics go a little bit faster. It's like knowing your times tables really well, or not knowing them quite so well and having to figure out a few of them as you move along. Question 15. True or false? Here come the true-false questions. Circle 1. Quadratic functions are sometimes odd. Are quadratic functions sometimes odd? Well, quadratic functions are in the shape of a parabola, always, whether they're upside down, right side up, whatever they want to be. I should say right side up and upside down. Whether they're really, really narrow or whether they're really, really wide, it doesn't really matter. The line of symmetry on a quadratic function always cuts right through the vertex. Okay, so there's definitely line symmetry in quadratic functions. We do not have rotational symmetry in quadratic functions. This question right here is false. Okay, and the directions said circle 1, so I'm going to circle and highlight both. Quadratic functions are never odd. Okay, they're sometimes even, and they're not always that either. Okay, question 16. True or false? Circle 1. If f of 6 equals 13, so that means that the point 6 comma 13 is a member of the function f, or is an element of f, or belongs to f, and negative 6, 13 belongs to f, well then f must be even. So what's even say? Even says that for all x in the domain, when you negate your x, the y does not change. So this is just a single example. And a single example is not all x values in the domain. So if I were to figure out that f of 6 equals 13 and f of negative 6 equals 13, I would say that f might be an even function, but I don't know that it is until I do one of those proofs that allows me to just put a negative x into the function and prove that I get positive f of x back again. So I can't say that this is true, and this said must be, and this is definitely a false answer right here. Okay, definitely false, because I don't know that it's going to be. It doesn't have to be, but it might be. Okay, proving this for just one point is not enough for a proof. You have to be very generic, and you have to prove it conceptually for all x in the domain. Question 17, true or false? Circle 1. If the input value of an odd function is negated, the output value does not change. So for an odd function, if you negate the input, the output does not change. That also is false, because the output always gets negated for odd functions. Okay, so that is definitely a false statement. Question 18, true or false? The graph of an even function must always pass through the origin 0, 0. And that's not true. Okay, I can come back up here and I can give you the picture for some even functions. Look at this even function. It did not go through 0, 0. Okay, we can go back up to the other questions that were up here where I gave you this funky graph. Oh, that was an odd. And this was even. I went through 0, negative 2. So you do not have to pass through 0, 0. Got it? Do not have to pass through 0, 0. Not for an even function. Okay, even function pass through 0, 0, that's not true. And what you can do is you can just give me a picture of something that's even. So I could give you a picture like the cosine function. Cosine function is even, but I did not pass through 0, 0. It passes through 0, 1. So this is what we call a counter example. And it's one word. I just didn't keep going to the side. But so here we are. This is another false statement. You do not have to pass through the origin. Okay, you could, but you don't have to. Question 19. Quadratic functions are always even. Quadratic functions say x squared on them, right? Quadratic functions are always even. If I had a quadratic function that were like this, then yeah, I would say, yeah, that's even. If I had y equals x squared, yes, I'd say that's even. Is it possible to have a quadratic function that does this? And if so, that function is not even. because that function is not symmetrical over the y-axis. If I were to try and draw the symmetry over the y-axis, that piece would come up here, this piece that would be the symmetry over the y-axis, and it doesn't land back on top of itself. So once again, false. Question 20. If g is an odd function, so we know g is odd, and g of 22 is equal to -3, so I have the point 22, -3 is going to be on g, then is it true that -22, 3 also has to be on g? What happened here? Negated the input, negated the output. That happens for all x values in the domain of odd functions. So this one is true. Right when you get used to saying false, 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 a true comes along. Question 21. All cubic functions are odd functions. Well, let's think about that for a minute. All cubic functions are odd functions. I do know that the common function that's the cubic function that looks like this, got a little whoop whoop going in there. I do know that this function f of x equals x cubed, that's odd. I can tell it has 180-degree rotational symmetry. But it's also possible to have other odd functions. That's the basic function. But I could do something that moves over here and has a horizontal and a vertical shift to it. This function is no longer odd because you don't rotate it around the point 0, 0 in order to fall back on top of itself. So all cubic functions are odd? No, that's not true. Not all of them are. Some of them are, but not all of them are. And question 22 is our last true-false. If the result of reflecting a function f horizontally over the y-axis and then vertically over the x-axis is the same as the original function, then f is odd. Let's see. If you reflect horizontally over the y-axis and then you reflect vertically over the x-axis, and it's the same as the original function f, then f is odd. Well, let's think about that. Let's just take a point, just any old point. I'm just going to kind of like think this one through a little bit. So I'm going to have my x-axis here and my y-axis here. I'm going to pick this point like 4, 1 or something like this. And I'm going to reflect it horizontally over the y-axis. That's going to give me -4, 1. And this is going to be true for all points, it says, right? If the result of reflecting the entire function f horizontally over the y-axis and then vertically over the x-axis, this would give me -4, -1. And that makes an odd function. That would make 4, 1 be called like point A, and then down here this would be the image. So look what happens. You negate the x and you negate the y. So that is absolutely true. A double reflection, or a reflection over each of the axes combined, does indeed end up giving you an odd function. That is a true statement, and we are going to highlight that. And we're going to go back and say one more thing about it. With an xy point, if you negate horizontally, or if you reflect horizontally over the y-axis, horizontally is going to give you -xy. And then you reflect vertically over the x-axis. That's going to give you -x, -y. The net result is, yep, you negated the x, and yep, the y negates as well. So that's true for every single odd function. You can look at an odd function and you can think, oh, let me flip it over the y-axis. Now let me flip it over the x-axis. And it doesn't even matter what order you do it in. It ends up being the same thing. Okay. Let's move on here. I have a cool activity that just took forever to create, so we're going to do this now. I have this chart here, and this chart goes down 7 blanks, okay? 7 blanks. 1, 2, 3, 4, 5, 6, 7, and then there's 3 graphs on the bottom of them. Now basically what I want to do is I want to take each one of these graphs on the right that I've created, and I want to decide to put them into the chart where it goes. So let's just grab one of these functions one at a time. I'll move them around as we go along. I'm going to take this first function here, this first function right here, and I'm going to spin my computer around so I can grab things nice and easily. And yes, I'm going to do that. Okay, so I'm going to select this function, and this looks like it has line symmetry over the y-axis. So I'm going to click and drag, and I'm going to put this where even functions go. And this is an example of an even function. I don't like the fact that it's hopping, so I'm going to press the Alt button, and I'm going to select this thing and move it really nice right in the center. Then let go of my slider before I release my Alt button. The Alt button is the first and last thing you push when you want to do that thing. Okay, now I'm going to look at this question right here. It is a function. Okay, I'm going to slide it up here and look at it nice and carefully. Does it look like we have line symmetry up and down the y-axis? And no, I don't think it does, because this point 7, -5 would be over here, right, if we were even. So no line symmetry. However, I do see that I am taking 7, -5 and becoming -7, 5. I'm going to alternate corners. So I wonder if I were to put my cursor right here at 0, 0 and rotate this function 180 degrees, it does indeed look like it would fall back on top of itself. This is an odd function. So I'm going to put it right in here where odd functions go. And I will just move it slightly and center it really nice. Let's grab this one. Let's grab this particular example and talk about this. What do we have here? We have a line. I have 9, -1. Question is, do I have 9, +1, -9, +1? So the answer is no, I don't. When I negate my x, the y didn't negate and it didn't stay the same. So this is neither. This is not odd and it's not even either. This is a neither category right there. Okay, let's grab this function and take a peek at it. I say function because it is a function, definitely. Okay, it's got a horizontal line to it. The equation of this function is y = 4. Any horizontal line, we've already discussed this, is definitely going to be an even function. So I'm going to go ahead and grab this and put it down here even. I definitely have line symmetry over the y-axis. Okay, let's slide that slightly more like that. Good job. Okay, let's pick any other one you want to try. What about this one? What about this function right here? Is this a function even? I said function. I shouldn't have even said the word function. I cringe at that. Okay, so for every x, do I have 1 y? And the answer is no. I can see clearly right here. I have 0, -4 and 0, 4. That means for the domain element of 0, it's paired with 2 different y values. That's not allowed in functional life. So I am going to slide this right over here and say neither. If it's not a function at all, then it certainly cannot be an odd function or an even function. Hopefully that makes good sense to you as well. Let's take a peek at this graph. Looks like I have line symmetry over the y-axis. You see the 7, -4 is over here at -7, -4. So the x values change and the y values stay the same. So the height of the function on the right of the y-axis is the same height as on the left of the y-axis. This is an even function, so I am going to go ahead and slide that right over here into the even column. What do we have here? I'm just randomly grabbing functions. This is a function because for every x there is exactly 1 y. It looks like I have rotational symmetry over this piece, but this other thing is doing something different than what it would do here. And look at, if this arrow is going down to the right, then when you do 180 degree rotational symmetry on this, it should be going left and up. Okay, and it doesn't do that. It doesn't do that at all. It goes down. So this is a down-down combination, which can never be odd. All right, I can't go down to -infinity here and go down to -infinity here and call this odd. Odd would have to be if I'm going to -infinity on the right, I'd have to be going to +infinity on the left. You see how I'm changing my x and y notations both. So I am going to grab this and put this in the neither column. And I see another function or graph right here. Let's see, what do we have? This is the line y = x. Okay, y = x, definitely if I take the point 8, and I rotate it 180 degrees, I didn't label it, but it's in there, right? -8 and -8. So I take 5, 5, and I rotate it 180 degrees, it's going to give me -5, -5. So I didn't label those points, but they're in there. Okay, this is good to go for an odd function. Y = x is odd. Yeah, maybe this needs to be just shrunk a little bit, but it fits right in there. Let's see, what is this thing right here? And I'm looking at, do I have line symmetry? No, because I have a bubble here and I don't have a bubble on quadrant 1. Oh, but it's down beneath here. So it looks like what was in quadrant 2 rotates to quadrant 4. It looks like what's in quadrant 1 rotated to quadrant 3. Yeah, this definitely looks like a odd function to me. So I'm going to put this in the odd function category. And I'm going to grab this over here, this graph. What do you know about this graph? Hopefully you know all circles are not functions, okay? So if you're not a function, I'm not even concerned whether you're odd or even, although I might get tricked into thinking if I rotate 180 degrees, it does fall on top of itself, and it does have line symmetry over the y-axis. However, we're not a function at all. So don't be tricked into calling something that's not even a function an odd function or an even function. What about this picture here? Does this look like this is going to be even? It does right here. I look at this big capital M and that looks even to me. Okay, I look like I'm going up to the left and down to the right, and that looks good. But this little thing has one little peak and this has two little peaks. This is kind of weird to me. If I turn this thing upside down, I don't even know if I can turn it upside down. Do you think I can turn this thing upside down? I don't think I can. That would be too bad. I'd like to be able to turn it upside down. Let's see if I can. Let's see if I can do something like this. Let's pick a new. Let's just grab it. Nope, I guess I can't. I don't know. I'm going to give it a try though. I'm going to try something new for me. So I'm going to grab this function. Nope, for some reason it's not letting me grab it. Okay, well, I guess I can't rotate it. But this is a neither category as well. Okay, I'm looking at the point 9, -3 becomes -9, 3. That's a good one. That's really good. But 11, 0 doesn't become -11, 0. Oh, did I plot that wrong? Let's see. Well, it's -10, 0. And this is 11, 0. No, these don't match right here. Kind of looked like it was going to match, didn't it? But it doesn't. No way. Okay, so this is a no on this category. As far as being odd or even, this is a neither category. So I'm going to have to find some room, grab it, and put it down here in my neither category. I'm having fun. I like this stuff. So I'm going to grab this picture right here. I'm going to slide it over. And I think this is like in your face kind of picture of something that's even. Look at everything here in quadrant 4 is the same as it is in quadrant 3. Everything up here in quadrant 1 is the same as it is in quadrant 2. Your points match up. This is definitely even. Okay, let's look at this one. What do we have here for the next picture? Oh, this kind of looks like cosine, except I'm going up to 5 and down to -5, but could be some kind of a transformed cosine graph. But definitely cosine is even. Let me see, I'm going up, down, up, down, up, down, up, down. Yeah, it looks to me like I have line symmetry over the y-axis here for an even function. And I would like to shrink that just a hair before I transfer it. There we go. Let's put it right in there. Good to go. Let's grab this function. I keep saying function. Is it a function? Yes. Okay, good. I'm lucky on that. So does this function look like it's odd or even or neither? Certainly doesn't have line symmetry over the y-axis, so it's not even. Does it look like I could take this thing and turn it upside down and end up getting the same exact function? I'm thinking 5, 4 here, -5, -4. That point works nice. 7, -4, -7, +4. That point works nice. 10, -1, -10, +1. That point works nice. Goes right through 0, 0, even though I didn't plot that. Yeah, I'd say this is a really good example of what we would call an odd function. Let's take a peek at this graph over here. This is a function as well. It's a quadratic. Okay, it definitely has a line of symmetry, but the question is the line of symmetry the y-axis? And the answer to that is no. So this would go into our neither column again. Here's a quadratic that is not even. And that was a good counterexample, right, for that true-false question that we had earlier. Now, what does this picture look like here? This looks like the sine graph, but it has some manipulation to it because I'm not going up and down to positive and -1. It does go through 0, 0. I think I clearly have 180-degree rotational symmetry on here, so that is going to make this into an, oops, let me grab it. It's going to make it into an odd function. I'm going to go in here and put it in the odd function column. Okay, what do we have here? Ba-da-ba-ba-bum. Looks like the McDonald's sign, doesn't it? So I am going to take this thing, I'm going to look at this, and I'm going to say, okay, looks like I am symmetric over the y-axis, so we got this left and right thing going on. The 0.47 is over here at -47. The 0.84 is over here at -84. Definitely symmetric over the y-axis here, so I'm going to grab this particular graph and put it over here into the even column. Okay, and move it down, make it fit really nice. Let's see, I only see one more graph over here, but I have 4 more places to fill in, so let's just grab this one. We'll play around for a minute. Looks like I have 180-degree rotational symmetry here. However, almost got me. This is not even a function. Look at this. I have the 0.04 here and the -4 down here. A function is a relationship where each x is paired with exactly one y. So I'm looking at this particular x value of 0 being paired with a +4 and a -4. That is not exactly one y. So therefore, this is an example of neither an odd function nor an even function, because it's not a function at all. I'll put that there. And I'm going to come out here and start looking for my other, oh, here we go. We got some pictures that are left up here, and we left up here. Let's bring these things over to where we want to be. Start playing around. Let's see, what do we have? Let's take a peek at this one right here. It's the furthest one. I'll drag it in. This looks like I have y equals, kind of looks like an x cubed function. As a matter of fact, it does, with a horizontal stretch of 3 or an r value of 3, which would mean a 1/3 inside the function. So the equation of this function would be y equals, open parentheses, 1/3 x, close parentheses, cubed. I definitely look like I have some 180-degree rotational symmetry going on here, so this is my odd function. This is an example of a cubic function that is indeed odd as well. So let me see, I think I have a space up here for odd, don't I? Here's my odd function, and it makes sense that perhaps I should have done that one first because it's a nice cubic function. Okay, what's this one? Let's take a peek here. Once again, kind of looks like I can spin this 180 degrees and 4, -6 would fall on top of -4, 6. Remember, if you change the sign of the x coordinate, you must also change the sign of the y coordinate. You're spinning around 0, 0, so the 0.00 has to be on your graph. I have a +6, +2, and over here -6, -2. This little horizontal ray is below the x-axis. Now it's above the x-axis. So it does look like things from quadrant 4 went into quadrant 2. Looks like this from quadrant 1 went into quadrant 3. This is 180-degree rotational symmetry, without a doubt. I'm going to put this over here in my odd selections, which means that this one over here has got to be the only one that I haven't filled in, which is an even function. Does it look even to you? It does to me. It looks like the y-axis is the line of symmetry, and if I were to take everything to quadrant 4, it would reflect into quadrant 3, or vice versa. Quadrant 3 would reflect into quadrant 4. Same thing with 1 and 2. So this is my last even function I'm going to throw in here. I think I'm going to actually blow it up a hair and just move it ever so slightly. Okay, and of course you would fill in an even function that's not the same thing as anything I gave you. Maybe a function that's neither odd nor even, or maybe something that's not even a function. And then over here, you should fill in an odd function and name some points when you're filling things in, okay? Name some points so that I can look at points to identify more than just shape. Okay, so I'm going to scroll back up here to the top. As a matter of fact, I think I'll shrink this down just a little bit. And I'm going to scroll back up to the top and double check all my answers to make sure that anything that I think is even looks like it's even. So I have an even function here. Symmetric over the y-axis. I'm still symmetric over the y-axis. This example, symmetric over the y-axis, looks like a mirror image over the y-axis. Every one of these look like the mirror image over the y-axis, don't they? Yep, yep, yep. Here, this is not even a function. I'm going to scroll back up. This definitely is a quadratic with some line symmetry, but the problem is the line symmetry is not the y-axis, so it does not qualify as an even function. This here, we got a couple of little whoop whoop, and over here, do 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 do. So nope, we don't have any horizontal or any 180-degree rotational symmetry, and certainly not the line symmetry either. If anything, I probably would have guessed line symmetry over the y-axis because this kind of talks me in, this big capital M looking thing. But then this messes it up here. This is like an upside down W, but I don't quite get the upside down W here. Not a function with my circle. And this is kind of looking odd, but then the ends mess it up again. You cannot have an odd function that starts low and also ends low. All odd functions will either start high and end low, or start low and end high. They have to do the opposite. Let me see, this is not a function at all, and this looks like a nice linear function. However, if I were to rotate this 180 degrees, the point 9, -1 would become the point -9, +1, and it's not over here. So no on that one. And then I'm dealing with odd functions. So 180 degree rotational symmetry is good on that, good here, good here, good there, good there, good there, and good there. Notice that in the functions that are odd with the 180 degree rotational symmetry, we are looking at each of these functions passing through the origin, because the origin is the point in which the function has to rotate about. Okay, that's it for me. I hope you've enjoyed. Talent out, you guys. Have a blessed whatever it is you're having. Day, week, year. Enjoy. Bye-bye.